Hi everyone and welcome to another example video. Today we'll be talking about powers of a complex number using the polar form. And let's take a number. Let's say z1 is equals to r1 e to the power I theta 1, where theta 1 is the principal argument and r1 is the radius of that complex number in the complex plane, or so to say the magnitude. Now if I want to raise this to the power 2, all I need to do is to write this expression and square it. So this means multiplying this expression 2 times, right? And this r1 and r1 will give me r1 squared, and this e to the power I theta 1 and this e to the power I theta 1 will give me e to the power 2I theta 1. In such manner, I can evaluate the nth power where n is any real number as r1 to the power n e to the power I n and theta 1. And this is also a polar form where this r1 to the power n can be written as a capital R, and this e to the power I n theta 1 can be written as a capital theta, or you can always denote it with a phi. So let's take a numerical example now, and we will also see that this is actually equivalent to the Cartesian form that we saw earlier. So let's take z1 whose Cartesian form is 2 plus 3i. Alright, so we have r equals to square root over 2 square plus 3 square, and this is 4 and this is 9, so this is square root over 13, and the argument is theta is equals to tan inverse 3 by 2. And if you numerically evaluate it, you should get the value of theta to be 0.98. So how can we evaluate z1 squared? Well, this is very easy. You have to write this r1 square and e to the power I theta 1 squared. Sorry, not squared. There should be a 2 over here. So you write r1 square as 13 because r is square root over this is r1. R1 is square root over 13. So if you square it, this becomes 13, and then you type e to the power 2i, and theta 1 is 0.98, and this is it. This is as simple as it gets. Then you just have to multiply 2 with 0.98, and if you do that, that is, you multiply this thing to have a full form, a full nice form, you can write this as 1.96, right? 13 e to the power I 1.96, oh sorry, 1.96, and this is actually equivalent to our Cartesian form. If you go to Cartesian form from here, if you want to go, so you write first 13 e to the power I 1.9, sorry, this is 1.96, I keep writing it as 19.6, 1.96, then this is what we are evaluating as z1 squared. Remember that, don't get confused with z. This is z1 squared, and we want to see that this is equivalent to the Cartesian form. So let's use the identity called De Moivre's identity, where we learned e to the power I n theta is actually equals to cos theta plus, sorry, cos n theta and I sin n theta. So now we want to see what is the Cartesian form of z1 squared. This is the thing we want to know, the Cartesian form. And we'll be using this polar form to get our Cartesian form. And then after this is done, we will evaluate the Cartesian form from scratch. That is, we'll write z1 is equals to 2 plus 3i, and then we will evaluate z1 squared. So first write z1 squared as 13 e to the power I 1.96, and then use the identity e to the power I theta is equals to cosine theta and I sine theta. So we will have cos 1.96 plus I sine 1.96. Now let's multiply 13 with cos 1.96, and we have to multiply 13 with sine I.96 as well. So let's see what does that give us. But first we need to evaluate the values for cosine 1.96. So, and if you do that, this will be 13 times minus 0.37. Obviously there are other digits, but let's just write 0.37 over here. And next we write 13 times sine 1.96, and if you evaluate the value for sine 1.96, you will have a 0.95. So 0.95, and if you add these two and multiply, that is, you multiply 13 with this thing and 13 with 0.95, and if you add these two, you should get 2 plus 3i squared. How I am saying this? Let's do it first. If we do that, so we want to multiply 13 into 0.96. So what is this 13 times 0.37 gives us? This gives us 4.81, and remember there's a minus sign, so this is 4.81, and here we can have 12.35. Now let's try to match this. As you can see, I have already written z1 as 2 plus 3i and z1 squared as 2 square minus 3 square, because this is coming from the formula for Cartesian powers that we discussed in the previous example video. And you type I, you type 2, you type x, and you type y. So as you can see, this is becoming 4 minus 9 plus 12i. Now you might say, no, this is 4.81 and this is 12.35. Well, the reason these are not exactly equal is coming from this part and this part, because this will have more digits in it, and if you take into account all those digits, then this is this will eventually become 5. So this is very close to 5, and here you can see this is minus 5 plus 12i, and this 0.35 will be negligible when you consider all the digits coming from this sine 1.96. that is, when you evaluate it, all the digits that will come from sine 1.96 will contribute in such a way that this will become 12. So this is another important thing to notice as well, because when you are doing numerical evaluation, how many places you take after the decimal symbol, that is the dot, will actually give you the accuracy limit. And from this example we can conclude that working in the polar form is rather easier than working in the Cartesian form, and they will eventually give us the same result numerically, provided we take appropriate decimal places. So this will be it for today, and thank you.